Hey kids, ready to do spherical coordinates, right? And you're like, no, stop. All right, remember we've already converted our 2D domain space into polars, right? And kind of like working on a circle. Then we went to when our domain space was 3D, we were like, oh, maybe let's go, right? Domain was 2 space. When domain was 3D, kind of made an analogy with working in cylindrical and kind of working within a space, right, oriented around the z-axis. Well, we can also sometimes work in spherical coordinates, which is instead of working around a cylinder, within a cylinder, it's within a sphere. So we got to define a couple of new things. Firstly, oftentimes this is convenient when your region involves symmetry about the origin, right? Instead of symmetry around the entire z-axis, just symmetry around the origin. I'm going to define a distance from the pole, right, or the origin out to the sphere as being rho, not the rho from math, right, from density. This is distance from the origin. And then remember in 3 space, remember in polars, we called the distance from the origin r, right? When we were just in polars, we called this r, and then we would rotate theta, right? And theta went from 0 to 2 pi. Well, now in 3D, we're still going to have that. And it's not like getting, you have to go through 2D to get to 3D. So we're still going to have an r and a theta, but I have a new angle up in 3 space. This angle phi is measured from the positive z-axis. The region that we're going to deal with again is either bounded by or is within a sphere. And our job is to convert between rectangular x, y, and z. That location, I want the same location, but I want to get to it with a distance rho, rotating in the 2D plane theta, rotating in the 3D plane phi. Phi goes from 0 to pi. So here's a picture. So again, this point in rectangular would be x, y, z. I want to get to that same location, but instead of going out x, out y, and up z, I want to rotate from the positive x, rotate from the positive z, and then radiate. Okay, so radiate out to a point and then nail where that point is up here in 3 space by fixing theta and phi. So my job is to figure out how do I get these values from x, y, z. Well, the first thing I'm going to do is draw this distance from my point in 3 space back to the z-axis. And then, of course, I have a right triangle there, so I hope it's not too much of a stretch for you to see that that is rho sine phi. Well, notice the next line I drew is red. And it's red because it's a z height, a z height. Well, hopefully that's not too much of a stretch either with this triangle that I drew up in 3 space to see that z is equal to rho who? Cosine of that angle up in 3 space. Right? Check. Now let's go down into 2 space. Now remember in 2 space, when we were dealing with polars, what did we call this distance that we radiated out from the pole? We called that r, didn't we? But look at the projection from 3 space here. The projection of this distance, isn't that what we used to call r? Just the projection? I mean, it's still r, but I can call it now rho sine phi. Hey, what's that in the XY plane? Isn't that how far out I went in the Y direction? And look at that right triangle. Can't you find Y? Isn't it true that cosine of theta is the opposite over the hypotenuse R, which we're calling rho sine phi? Can't you get Y by itself there? Oh, I said cosine, I meant sine, my bad. And can you do the same thing then with X? Cosine of X, or cosine of theta, which involves X, is X over that radius, that R, but I'm involving the three-space angle in there. So Z is equal to rho sine phi cosine theta. And if you remember from polars, what was our conversion from polars? Right? Wasn't our conversion Y is equal to R sine theta and X? What the heck? Why can't I write? X is equal to R cosine theta, right? It's just that now our R, bringing down our projection from three space, is rho sine phi. Check, check. So the only thing I haven't done here is our distance rho. Well, what is that? Isn't that x squared, project this y, right, y squared, and z squared? Right? So of course, rho is the square root of that. And we're dealing with positive distance, so we just need the positive square root. Well, that's crazy. Here it is written a little neater. Remember, R comes from that side of the triangle up in three space, rho sine phi. X we've always known as R cosine theta, and Y is R sine theta. We're just getting our Z space in there. And then Z is the side in three space that dealt with, right, the triangle that had phi in it. So it was rho cosine phi. And then, of course, here's our Pythagorean relationship for rho. So before we do any calculus, let's just practice converting. So if you want to pause the video and do this without me, go ahead, or you can just continue with me. In spherical, this is rho, theta, and phi. I want to go to rectangular. Sine phi, cosine theta, rho sine phi, sine theta, rho cosine phi. So I'm sure you can do this math just fine, and you end up with the same x and y coordinates, and z equals 1. Now, can you picture this? If I go out the same x and y, and then up to 1, do you believe that's the same position as I would get if I had a length of 2 from the origin and I nailed it down by rotating pi over 4 units from the x, and pi over 3 units from the y. Right? Hope, even with my really, really poor drawing, that that's not too bad to see. So let's do the other way. Let's go to spherical. So for spherical, rho is the square root of 0 squared plus 2 root 3 squared, which would be 12, plus negative 2 squared, which would be 4. So that's nice. My rho is just 4, square root of 16. Z then is equal to rho cosine of phi, but you know the z, don't you? So plug in z there, and we know rho. So you're looking for an angle that has a cosine of negative a half, so phi must be 2 pi over 3. Now let's go get, I can go get x or y from here, right? But I might as well, since x has a 0 in it, right? X is equal to rho sine phi cosine theta. Solve that for cosine theta. When you put 0 in for x, you're going to divide by 4 sine 2 root 2 pi over 3, but it's not going to matter because you have 0 in the numerator. So theta is equal to pi over 2. So can you visualize that? If I go 0 in the x direction, 2 root 3 in the y direction, and then down 2 units, right? Imagine the z-axis is going down 2 units here. Does this position, can you buy the fact that if you radiated out a distance of 4 from the, right now you're going down 4 units, that is rotating pi over 2 units in theta, but rotating down 2 pi over 3 from the z. Again, my drawing's pretty poor, but I hope that you can visualize that. How about this one? Collect your x squared, y squareds, and z squareds, because you know what that is equal to. And I don't care whether you keep the 2x on the left or the right, actually, whether you either still say this is equal to 0, because that's certainly rho squared is equal to 2 what? If I really wanted to get rho by itself, I would take the square root of that, right? All right, let's do some calculus. So we need to, we just spent time thinking about if we were given a function in x, y, z, we could transform it into rho theta phi. But we also have to transform our dv. So there's some cool calculus and geometry, really. I shouldn't even say. There's some cool geometry in how this partial change in, or this little change in the volumes as you add them up, and here's my change in phi and my change in theta and all that kind of stuff. How that works out to get here. You don't really need to know that. Look it up if you're really interested in it. But what I really want you to focus on here is the price. Just like in polars and cylindrical, we have a price to pay for transforming from our dv into spherical. This is the price we have to pay, right? And then we're going to take the integral, and of course, all these deltas are going to shrink to d's. But this price, anytime you transform from dv, you have to include that now in your integrand, just like you did with the r's with polar and cylindrical. So let's evaluate this E space, whatever this is, upper half of a sphere. This sphere, I hope you can see, has a radius of 1. I'll do a very, very poor drawing of it. Right? Right? Imagine the others, right? Got to go around in the back too, right? Because it is the top half of the hemisphere. So what do I need to do? Step 1, pay the price, right? I'm going to take this dv, turn it into d rho, d theta, d phi. And this is just tradition to, again, you can, it doesn't matter the order that you do these in as long as you line everything up. D rho is always first. I've seen these two switched around. But pay the price. Determine my bounds. So determining the bounds, hopefully it's not too bad for you to see that I just have rho squared is equal to 1, therefore rho is equal to 1, right? So from the origin, anywhere out that I'm radiating to the top of this sphere, hemisphere, to the bottom. What's the bottom going to be though? Right? The bottom is just where z is equal to 0, right? So this is, right, where this is the equation, my hemisphere equation. This is z equals 0, but I'm in rho. So what is my rho going to go from? 0 to 1, right? Origin out to the surface. Then I need to think about how am I rotating to get the whole surface from the positive x-axis? How do I get this whole hemisphere? I hope that's not too bad to see. And then d phi from the positive z-axis. Remember, phi goes from 0 to pi down here. Do I need any of this? Right? Phi goes from positive z-axis, 0 to pi, all the way down here. Do I need, I'm not underneath there. So what is my phi going to be? That's just going to go from 0 to pi over 2, right? So here's my distance out to the origin. Here's me rotating all the way around in the xy plane to get the entire hemisphere. But then since phi is 0 to pi, and I only have a hemisphere, I only need to go to pi over 2, right? This distance here. So there's my bounds. Notice what I've highlighted in the integrand though. Make sure I've lined everybody up. These are rho values. These are theta values. And these are phi values. What do I have to do to my integrand? Right? Z is equal to rho cosine theta. Make sure you, right? Everybody's got to be transformed. Now I'm going to look at that, and especially with all my limits of integration being constants, and my integrand is a product, I think I'm going to break this up, right? Into, right, instead of doing iterated, I think I'm going to do my 3 separate integrals. So, I mean, I really could have kept this 16 anywhere. I could have even moved the 16 all the way to the outside. But notice that I have p cubed right there. I didn't have any expression in here that had theta in it, which is why I just have a 1 d theta. And then I collected everything that had a phi, right? So I have a phi here and a phi there. So this integrand, right, this integrand is just going to be 2 pi. Here you're going to have p to the 4th over 4. And then that other one, if you trust me, right, I'm going to use u substitution on that. This one is just going to be 2 pi because it's the constant. And this I'm going to use u substitution on. And I am just going to get, when I'm all done with this, 4 pi. Please go ahead and try to verify if you'd like. Next one. Same thing. They want me to evaluate. They give me an integrand that is not just one, so I'm not dealing with just, a 3D volume. And this time they're telling me the space they want lies between two spheres. So since I'm between two spheres of radius 1, and radius 2, right? What's your top minus your bottom? Pay the price. I'm going to have to go over x squared and y squared. I'm going to have to transform them as well. What are my bounds? And rewrite my integrand. So my bounds, as I said, I'm dealing with rho. Rho is going to go from what? 1 to 2. Right? Because I have my radiate out to the lower one, radiate out to the higher one, top minus bottom. Now what about theta? Right? Theta is in the positive x. How am I going to get the entire spheres? Where am I going to rotate? And what about phi? I need to get, right? Phi is measured from here. Right? Theta was from the positive, right? I needed to go all the way around. Gets me my whole spin. What about phi? I need to go all the way from 0 to pi. That's terrible. Whoops, sorry. Now I'm going to replace the x and replace the y. Pay the price. D rho, d theta, d phi. And this is going to be rho sine phi cosine theta. And this is going to be rho sine phi sine theta. And then, of course, my price, rho squared sine phi. Now, when I do some nice algebra happens with this, hopefully you can see you're going to get a sine squared and cosine squared. So I'm going to end up with a rho squared sine squared of phi times a 1. That comes from my cosine squared sine square of theta. And then I still have my price. So I end up integrating here with an integrand that is rho to the 4th and sine cubed. So I wanted to do this one because integrating sine cubed is going to take an identity that I don't expect you to know. I had to look it up as well. But again, with an integrand, with limits that are all constant and an integrand that is a product, I actually did 3 integrals. And again, since it's all multiplication, doesn't matter the order. I took care of my theta, which I know is just going to get me 2 pi. Then I did my rho. I just have rho to the 4th. And then I had my phi. So the identity that you need, and I would give you this, I wouldn't expect you on an assessment, or just not give you a problem that needs this, but I didn't want you to struggle with this. This actually isn't so bad. Right, because now I'm going to distribute, and then I'm going to be able to use U substitution on that. And of course, this is going to be p to the 5th over 5, and that's just going to be my 2 pi. And when I'm all done, I ended up with 248 pi over 15. All right, one more. This one just asked me to convert, didn't ask me to evaluate. So this time, notice the other 2 examples, I was given a shape and told what the shapes were in 3 space, right, in the equations in rectangular, but now I'm giving the actual problem already put into rectangular, and they want me to convert the whole thing into spherical. So I plop down the formula here with the price to pay already. And this is an ice cream cone. How do I know it's an ice cream cone? Well, I looked at my bounds. Remember, this is dz first. So z is equal to a cone. Z is equal to a sphere. Right, top of the sphere. Now look what's next, x. So this is x equals 0, and x equals 9 minus root 2. Lastly, y. These are my y bounds. So can we think about what's happening here? So if I just look here for xy information, this is my 3D information. So I kind of got my top minus my bottom. So I know what, right? This is not too bad to convert to rho, right? Right, if you have z is equal to the square root of 18 minus x squared minus y squared, z squared so x squared plus y squared plus z squared is equal to 18. Therefore, rho squared is equal to 18. Rho is then equal to the square root of 18, or 3 root 2. Don't care how you do that. So Z is going to write, this is at my origin, Z is going to start at 0, sorry, and then rho is going to start at 0, and rho is going to go to 3 root 2. Now look at what's happening in 2 space. In 2 space, my x values are going from 0 to this curve. What is that? Right? Isn't that a sideways parabola? Just this piece? With a radius of what? 3, right? All right. So if I'm only going from right, the x, that's on my, that, remember, that's on the xy plane. But wait a second, look at y. Y is only going from 0 to 3. So this is the only portion that I care about. So can you represent that with my theta and my phi? Right? I don't need, oh, so what's happening on the, right, I'm doing, so I took care of d rho. What about d theta? What's my theta going from the positive x-axis? How far am I rotating? Right? Now what about this phi? How can I see that? Well, if you can't, if it is hard for you to visualize, here's a way for you to think, right? Phi, think about all your conversions. Who had phi in it? And only phi in it? Z, right? Isn't it true that Z is equal to rho cosine of phi? So the Z, remember, I want the Z to be, here's my axis. I want to, where do I rotate? I want to know where these guys meet. Right? Where is that? Where do they meet? Can you tell me where the two of them meet? Right? Where are these guys going to meet? After I get rid of the radicals. Two x squared plus 2y squared is going to equal 18. Divide everybody by 2. Hey. Right? Oh, wait, that's what I knew, right? So when I'm looking at the projection, 3 must equal 3 root 2 cosine phi. So cosine phi is equal to 3 over 3 root 2, which is 1 over root 2, who has a cosine of 1 over root 2 pi over 4. Right? And hopefully that makes sense here, where you're rotating down to right? The cone is cutting up through that space, right? And it's cutting, right, the whole rotation comes, right, all the way down to pi, but I'm not even, as I come down here, I have to, that the line of the cone there cuts off, right, cuts off part of the hemisphere. Now the only thing, so I've done my bounds, what else do I have to do? I have to transform here, and I already had done that before, so x squared plus y squared plus z squared is just rho squared. So this was rho squared, and then remember the price I had to pay was rho squared sine phi. So that's where I got an integran of rho to the fourth sine phi. And then of course I would split this up again with all my constants and a product here. That'd be pretty good. All right, that's it. So we'll have some fun with this when I see you on our next live session. Bye.